It's the crankshaft. The crankshaft's horrendous. So one of the TX2Ks, I was standing on the line with Ken Gummis from ETS, the engine builder. The very first pass off the trailer, Ken looks at me and says, "If we pull that down now and mag the crank, it's cracked."
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Chris from Crest CNC in Australia. Now, over the last 10 years or so, I've seen an absolute explosion in manufacturers producing all manner of flash, shiny CNC components for performance engines. And this could be anything from a full billet block, which obviously has changed the game, particularly for those looking for huge power numbers for drag racing and roll racing. But right down to billet sumps, billet rocker covers, billet oil pump assemblies, the list is literally endless. Interestingly though, with Crest CNC, they've actually transitioned towards cast components, which might sound a little bit strange from a CNC shop. In particular, they came onto our radar because of their cast heads for the Subaru EJ series engine. On top of this, they're in the final stages of building their cast Nissan RB26 blocks. They're also looking at building cast blocks for the Subaru EJ as well. So you might be asking yourself, why does a CNC shop put so much effort into making cast components? And that is a question that we put to Chris as we go through this interview. Before we get into our interview though, for those who are new to the Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build engines, how to tune engines, how to construct wiring harnesses. We also cover 3D modeling and CAD, race car setup, race driver education, just to name a few. You can find all of our courses at hpacademy.com/courses, and all of our courses are delivered via high definition video modules that you can take from anywhere in the world, provided you've got an internet connection. This gives you the benefit of being able to learn from the comfort of your own place, and you can learn at your own pace. All of our courses also come with a 60-day, no questions asked money back guarantee. So if you decide it's not quite what you expected, let us know. We'll give you a full refund of the purchase price. And as a podcast listener, you can use the coupon code podcast75. That will get you $75 off the purchase of your very first HPA course. We'll put a link to our courses page and that coupon code in the show notes. Lastly, if you like free stuff, then we've got a deal for you. HPA partners with some of the biggest names in the aftermarket performance industry to run giveaways all of the time. This might include an aftermarket ECU or dash, maybe a power distribution module, maybe engine building tools, maybe wiring tools, or anything else in between. In short, this is a prize you absolutely will want to win. And if you get your name into the draw and you do win, we will ship it to your door free of charge anywhere in the world. There's also absolutely no catch, no purchase required. So you can head to hpacademy.com/giveaway to find out what our latest giveaway is and get your name into the draw. All right, let's get into our interview now. Right, welcome to the podcast, Chris. Thanks for joining us today. And like we always do, let's start by finding out a little bit about your background and specifically how you got an interest in the automotive industry.
All right, I'm an engine reconditioner by trade, but I've always had a focus on manufacturing instead of reconditioning. Bought a CNC machine around 2010, started making billet intake manifolds, but always had a passion for manufacturing blocks and heads.
All right, I feel like you've gone from 0 to 100 real quick there, so let's just rewind a little bit. Starting with the process of becoming an engine reconditioner, how does that actually work in Australia? What do you need to do?
It's an apprenticeship. My trade was basically split between the mechanics and the fitters and turners. So I'd spend a week with the fitters and turners learning how to machine, and then I'd spend a week with the mechanics learning how to bolt things together.
On that note, is learning machining operations sort of typical that every engine reconditioner is going to go through? And on that side of things, are you talking specifically about just the very specialized machining operations that are used to recondition an engine, or is this more general sort of lathe and mill operation?
In my situation, there wasn't many engine reconditioners in my class at all. So I had to learn gear cutting, thread milling, all sorts of general machining operations that a fitter and turner or toolmaker would learn.
Am I right in saying that that would be therefore above and beyond what the norm would be for an engine reconditioner?
I think so, yeah, that's correct, yeah.
It sounds like it's obviously set you up in good stead for what you're doing today, though. Another topic in terms of engine reconditioning, and this is sort of something that crops up on the podcast from time to time, as I've seen it personally, there's quite a disconnect between engine reconditioners and those who are building performance engines. Now, obviously, yeah, there's a lot of cross-pollination there, but what I'm getting at is these days, a lot of the engine reconditioners that are kind of rebuilding garden variety, everyday pedestrian car engines, the tolerances, clearances, the skill level required to rebuild an engine that's maybe producing 30 horsepower per litre or something quite low, quite different to a race engine that might be producing, sort of a couple of 100 horsepower per litre. Do you agree on that?
Yeah, I do, but I think it's all up to the individual person. So back where I used to work, Hunter engine reconditioners, I worked with guys who didn't care about engines at all. They just saw it as a paycheck. And then I worked with guys who would finish their normal day job, go home, fire up the flow bench, start porting, and that kind of led from there.
Yeah, so I mean, this sort of differentiates between a job and something that you're passionate about.
That's it. Yep.
On that note, sort of if we come back a little bit before you decided to become an engine reconditioner, am I right in assuming that you developed your own passion for cars?
Yeah, for sure. I'd always been interested in cars and engines. There's so many engineering disciplines to make a high-powered engine work. You've got metallurgy, tribology, CAD design, everything that's required to make a high-powered engine work needs to be at the top of the game. So that interested me a lot.
Sure. Metallurgy, I think probably most people could get their head around what that term means. Tribology, though, let's break that down. Not one we hear too often on the podcast.
It's the study of sliding surfaces. So cam on lifter, threads, for instance. Tribologists are designed in fastener manufacturing, things like that.
So this is something you had to study and understand to be able to work at the level you wanted to?
To be honest, I'm interested in it, but you can only choose to, so much that you actually want to focus on to be good at something. You don't have the time to be a guru at everything.
No, sure. All right, catching back up with your story, you sort of just glossed over the fact that you went out and bought a CNC machine and then started your own company. Can you kind of bring us up to speed? I'm assuming that just going out and buying a CNC machine is that's probably the easy, if not the more expensive part of that operation. How did you transition the skills and knowledge that you had from conventional machining into CNC? How steep is that learning curve?
It was pretty steep for me, but at the time I had a good friend of mine who worked in defence, and he taught me a lot. I was working for BHP at the time, doing say week on, week off, so that was pretty good. It allowed me to focus on CAD and CAM, and I learned a lot from my business partner at the time.
Okay, so CAD and CAM go hand in hand with CNC machining, and this obviously, for those who haven't been involved, can be a bit of a steep learning curve in and of itself. So, how did you build up those skills? What was the process you went through to learn those techniques and software packages?
So, always been interested in engines. Kept on getting asked to make billet intake manifolds, and that's the big one. Is to actually learn the software, you need to have a project. You can't just go, oh, I'm just going to learn the software. It's like you need to have something that you're interested in. So at the time, we didn't have much measuring tools. We just had, the basics. So started pulling down motors, working out the bolt pitch, drawing up intake manifolds.
At this time, I'm guessing you're doing this manually. You're not reliant on the technology that we have now, 3D scanning?
Yeah, so back at World Time Attack, I think Connor interviewed a guy that works for me, Jerry Whelan. He was talking about scanning technology. Jerry, at the time, didn't mention it, but we've actually got our own in-house CMM now. So we rely on that more so than anything, more so than scan data.
Okay, let's back up for those who haven't heard the term CMM. Can you expand on that and then give us a differentiation between that and laser scanning?
Okay, so a CMM is a coordinate measuring machine, and it's got a probe. So we probe all the dowel holes, the planes, the bolt positions, the bores, ports. So it's actually a physical contact, and it's a lot more accurate than a 3D scanner.
So in terms of the options we've got for scanning these parts or turning them into a digital part, you've got laser scanning technology, and this starts at the simplest, I'm guessing, would be using your cell phone. And we've talked about this over on the HPA Instagram in the past. There's software or apps that you can use for using the LiDAR equipped in your phone to take a basic scan. And of course, the accuracy is not going to be the same as the more expensive products. At HPA, we've got a Peel 3D scanner, which I think we paid maybe around about $10,000 for. I think we actually bought it secondhand, but I mean, that would be considered more at the entry level of 3D scanning. And then, it's easy to sort of spend $100,000 or more. So could you give us some broad understanding of like what kind of accuracy we're going to get with those options? The cell phone versus maybe an entry-level laser scanner versus a high-end laser scanner versus your coordinate measuring machine?
Okay, so I'm not too sure about the phone. I think that could be millimeter accuracy. I don't think it's less than that. The 3D scanners, I think more like quarter of a mil, and my CMM is good for around 0.025, so about 1,000.
Yeah, significantly better.
Yeah, but the high-end CMMs are good for microns, so 3 decimal places.
Like anything, you're going to get what you pay for, and it really comes down to, I guess, deciding on the accuracy that you need for a particular task.
I believe so, and also a big thing that I don't think anyone talks about is trying to work out the designer's intent. So you could have all the data in the world, but you can't just start putting bolt holes or dowel holes directly on your CMM data or your scan data. You need to try and work out what the designer's intent was, whether that was in imperial, whether it was in metric, whether it was in fractional imperial. Damn Yanks still continue to use weird fractions.
Yeah, you're probably upsetting a large portion of our listener base, which is based in the US, but I couldn't agree more. I think even coming from New Zealand, where the metric system rules supreme, when you get into the game of engine building at any level, your arm pretty much gets twisted and you're forced to be able to understand both metric and imperial units. So I kind of can work in both. I don't say that I like imperial, but it's kind of a necessary evil.
I pretty much did my apprenticeship in imperial, and whenever I build an engine, I'm always looking at thous and feeling thous. But when you start talking about CNC machines, all my CNCs are set to metric, because once things start to go over a foot, as a New Zealander or Australian, what are you going to do? You're going to start talking in yards and miles. And
Absolutely not.
no.
Yeah, I come back to the meme that's sort of done the rounds number of times of the metric system versus the crazy roller coaster of imperial, and that is kind of the reality. But again, it's what we're dealing with. So I always say that the imperial system isn't too bad if you just remember simply that there's 25.4 millimeters in 1 inch. That kind of sets you up, and everything else can be done on your calculator. So pretty easy to convert if imperial is not your thing. Now, I asked about software packages, and we sort of glanced over that. Obviously, there's a lot of software available. First of all, for the actual design process, what have you sort of gravitated towards?
Okay, so I use a software called Visi. It's from Vero Software, which is based out of the UK. It's a tool and die software. Not many people have heard of it, but very powerful cam. It's got 5-axis simultaneous cam, which is handy for CNC porting.
Okay. Where do the advantages lie in that particular software compared to the more conventional that maybe our listeners would have heard of, Fusion 360, SolidWorks, for example?
So I basically gravitated towards Visi because that's what my partner was using back in the day in defense. Back then it was quite cheap. Now it certainly is not. And all the extra modules that I've got adds up to potentially about $80,000 worth of software.
Obviously not suited to the home enthusiast.
No, it's not. If I was to start again for a cheap software, probably would be SolidWorks or possibly Fusion. Yeah.
Okay. So you mentioned modules. How does that work? What are these modules that you buy?
Okay, so for Visi, there's a basic 3-axis package where it's all just basic toolpaths that some of these users would be familiar with. And then the 5-axis simultaneous package adds an extra about $15,000 to it. And then there's a lot more other modules that you can tack on. I think one of them's actually called shoes. So there's a tab at the top called shoes, so you can design your own, tooling for shoes. But it's obviously something that I'm not interested in.
Clearly not. Okay. I guess that's the thing we do need to understand with these technologies is that we're very focused on the automotive industry, but I mean, it's prevalent across just about every industry these days. Now, you've talked about 3-axis and 5-axis simultaneous. So am I right in suggesting this is the CAM part of the software? So we've got two elements here. We've got the actual design, the 3D modeling side of things, which is where you're actually going to create your part in the virtual world, but then the process of actually machining that requires that part to be converted into tool parts that the CNC machine can understand. Am I sort of getting that correct?
Yeah, it's correct. So Visi's all in one. So if I'm machining something and I go, oh no, I want to change something, I can just do it in the same package, where a lot of other packages, they're separate. So you've got CAD, which is computer-aided drafting, and then you've got CAM, which is computer-aided manufacturing. So having them in the same package makes it a lot easier for me.
And with the manufacturing side of things, the tool parts, how automated is that? How much input does that require from you to get it right?
Depending on the complexity of the part, it varies significantly. You can spend weeks programming just one part, such as an engine block or cylinder head.
And is that all manual or is there some automation element? I'm just trying to get a sense here of sort of what is required from you to get this across the finish line and be able to send it through to your CNC machine.
So basically, we designate a boundary to stay the toolpath within, designate the Z height to stay within that, and then we tell it if it's going to do a step down or a step over. Yeah, there's a fair bit that goes into it. It's a bit hard to explain, to be honest.
Sure. Yeah, no, fair enough. Okay, so coming back again to you actually learning these software packages, what was the process you went through? How did you actually get to sort of master these? You mentioned sort of starting out with the design of an intake manifold, but I'm guessing you probably sort of just didn't sit there in front of the computer screen and kind of blindly figure it out by yourself.
For the most part, I did. Yeah.
Okay.
I had a little bit of input from the software reseller and a bit of help from my business partner at the time.
All right, so once you'd sort of got your head around how to actually use the software and your CAM software, you're ready to actually essentially make your parts. What was the learning curve from the first part you made and the problems you found along the way? What did you need to improve in your processes?
Trying to work out what tools to use was the biggest thing for me. Coming from just being an engine reconditioner, we never really had that access to many different types of tools, where if you go into CNC, there's all sorts of different shapes and processes that you can use.
And I'm guessing each of these tools as well comes with a fairly hefty price tag, so you don't want to just equip your CNC shop with thousands of available tools?
Yeah, that's correct. Back then, I only had maybe $5,000 worth of tools, where now I've maybe got $500,000 worth of tooling alone.
So everything in the CNC world comes with a fair few zeros at the end of it, obviously.
Yeah, it can get out of control pretty quick.
All right. Let's step back a little bit. So once you decided that starting your own CNC shop was your game plan, you've at this point bought a CNC machine and you're learning this. How long did you sort of take before this was a full-time deal for you?
I worked at BHP on and off whilst I was learning this stuff. So
you mentioned week on, week off, so it gives you a good amount of time to get stuck into your passion project?
Yeah, that's correct. So I was there at BHP for 8 years, and for about 5 of those years I was doing the CNC on the side as a bit of a hobby, to be honest.
And at what point did you sort of know that the time was right to go full-time and commit and dive right in?
Once we realised that no one else at the time, back in say 2015, were actually manufacturing the Billet VR38 block, we purchased more 5-axis machines and started doing that full time.
Okay. So the VR38 was your first Billet block project?
Correct. That's right.
All right. So this is a very popular platform. Obviously, hundreds of people around the world drag racing these and half-mile racing, and the power numbers are sort of I guess now well north of 3,000 horsepower, I'd assume, looking at the trap speeds. Where does the problem come in with these VR38 blocks? Because before we started recording, you sort of mentioned you cut your teeth on these blocks as an engine reconditioner building performance engines and found some problems with them.
Yeah, that's correct. So with the bore lust, everyone wants a bigger bore. People fit wet sleeves. They remove all the structural integrity from the block, and then the tensile loading in the block just cracks down the side, and then that necessitates the use of a billet block.
Okay. So this is sort of a pretty common path, I guess, with a production aluminium cast block is at some point, even if we look outside of the problem with wanting a bigger bore, which the factory sleeves and liners can't support, at some point we generally see problems at very high power and boost levels. The actual cylinder pressure can either flex the existing sleeve or in some circumstances crack it. So then the move to a ductile iron sleeve is the general sort of next step forward. But as you mentioned there, you're actually removing all of the structural integrity, basically machining the entire guts out of that VR38 block in order to be able to fit these wet sleeves, correct?
Correct. That's right.
You're fixing one problem, but creating an even bigger one.
Oh, yes, for sure.
And on that note, I'll reference back, and my memory might be a little foggy on this, but we had Tony Palo from T1 Race on the podcast a fair while back, and maybe we can link to that particular episode as well if people want to listen to it in depth. But he had that same problem, basically went down that well-trodden path with alloy blocks. All right, we'll machine everything out of the middle of it, put in a sleeve, and found that same problem you're talking about with the blocks cracking. If my memory serves correct, they actually went back to the factory block unmolested, and I think he was up around 1,800 wheel horsepower with no signs of problems. And the only reason they actually went billet was for the ability to run these bigger bores. So with the move to producing your own billet block, if my memory is correct, we were talking about this before we started recording, at the point you started this, there were no billet VR38 blocks around?
Yeah, that's correct. So when we were cracking blocks, I contacted all the people on the internet that said that they were going to make a billet block, and I just didn't get any response after multiple emails and phone calls. So I said, that's it, we're making our own, and here we are.
So you were actually first to market with the VR38 block?
Correct, that's right. It was actually under a different name back then. I had a different business partner back then, but I've dissolved that company now and just gone back to the original name of Crest CNC.
Okay. Well, let's get an understanding of what the process looks like. I mean, these days, billet blocks are, I wouldn't say the norm, but there's a range of manufacturers around the world producing them for a variety of popular platforms. So they're certainly not uncommon these days. But when particularly you don't have a competitor's product to look at and you're kind of starting blind, what is the process of turning that factory cast alloy block into a billet version?
So we knew the failures that we're having. So we could tell that it was cracking under tensile loads more than anything. So we beefed up the sidewalls significantly, and also going to a 6061. That improved the mechanical properties a fair bit compared to the casting.
All right, well, on that note, I'm not a metallurgist, but let's talk through that 6061 aluminium alloy versus what is used in a cast OE alloy block. What are the differences?
So tensile strength for the casting is a fair bit less than 6061, and for the really hardcore ones for 3,500 horsepower, we actually go to a 7075 material, which is potentially twice as strong as the factory casting.
Okay. Any downsides going to a stronger material? Is it just cost, or do we sort of get this way off with strength versus maybe it becomes more brittle, something like that?
The elongation for 7075 versus the casting, it's actually got more elongation. So 7075 certainly isn't a brittle product compared to a casting. So there's just a lot more strength available there.
Okay. In terms of getting the actual design again into the computer to start working from, I'm assuming back then you didn't have your coordinate measuring machine. What are you relying on to get the basic dimensions and specifications of the block?
So we subbed out the CMM work on the VR38 block to a known aerospace company that's local, and that was a high-end CMM which gave us very accurate data.
So you can be confident that you've got all of those key points in exactly the right spot. Because obviously you don't want to end up producing a very expensive block and then someone goes to bolt the cylinder head on and finds that your head stud locations are, half a millimeter out or something like that, correct?
That's correct, yeah.
The other element with this is when you're designing these blocks, obviously you've got complete freedom in the entire design, as long as it's obviously going to house the factory crankshaft, for example, and bolt the heads on. How much consideration do you take into about the ability to bolt on all of the normal ancillary components to the outside of the block? I'm talking here about engine mounts, alternators, etc., all of the other things that kind of fall outside of the main structure of the block. How important is that?
Yeah, so that's one of our main goals, is to maintain compatibility with everything else in the car and components. We don't mandate electric water pumps or dry sump setups. We try and maintain everything that bolts on. So if there was an M6 on it somewhere that held the loom clip, we put that M6 there, because you don't want your loom clip dangling down, getting caught up in drive shafts and things like that.
Sure. Is there also a bit of a balancing act here, because making the side of the block, for example, nice and sculpted so that you're maintaining an equal wall thickness around bores or around ribs or whatever that there might be, versus just a plain flat surface that's going to be much quicker to machine but also going to have more material and more weight. So do you kind of have to weigh up those pros and cons?
We do, but there's no way that I'm going to produce a block that looks like a filing cabinet.
So form and function sort of do still go hand in hand when you're making these parts. You could make a block that, for all intents and purposes, does the job but looks ugly, and that's not going to fly.
Nah, that's, we've got the software. We know where the radius buttons are on the software. We use the radius button. Yeah.
All right, so when it comes to producing a block that is for a dedicated drag car, I'd argue, or I would assume, that that's relatively straightforward, because water jackets aren't necessarily going to be required, particularly if you're running on methanol fuel. Start it up, burn out, run down the strip, and then it's probably going to get towed back down the return lane and be shut down. So that's not so bad. When you're doing a block that also needs to remain streetable, or for maybe a road race application where it does require coolant, I could only imagine that being a massive undertaking when you're designing a CNC block. What's the complexities there, and how do you go about doing that?
Yeah, so every single billet block or billet head that we've ever made has some level of water in it, and that is the major complication on getting the water where it's needed, sealing the water jacket properly, and that is a major reason why we've started looking into castings.
Okay. All right. Before we talk about castings, let's come back one step. So I'm interested, you mentioned it is a complexity, it's obvious, but if you are doing an all-out drag block, why still maintain water, or is it just so you don't have two completely different block designs?
A little from column A, a little from column B. So I mentioned ETSG before. That motor is still fully water jacketed.
So this is the Extreme Turbo Systems.
Correct, 3,500 horsepower VR38, that's right. So that can do a run, come back down and do another run straight away. There's no waiting for fans to cool the motor down or anything. They can just do run after run.
Yeah, okay. I remember actually I had the rare privilege to interview JR from ETS, and I think that was at Pikes Peak Airstrip Attack many, many years ago. And he sort of talked about the reliability of the mechanical components in the engine, because as a casual observer looking at videos of these cars doing their thing or reading articles about them, we kind of gloss over the fact that at 3,000 plus horsepower, there's a finite life on the engine components. And again, I can't remember the specifics, but I think he was talking somewhere in the range of about 20 passes, and I'm talking half-mile passes here on the rotating assembly before basically everything got binned and replaced. Likewise, the heads were also requiring a fairly expensive maintenance schedule. What's the life expectancy of a billet block? Is that essentially infinite as long as you don't punch a couple of rods out through the side of it?
Yeah, so the very early version of the VR38 billet block that we made was quite thick and chunky. I don't think ETS have ever binned one. They've done hundreds of passes for the last nearly 10 years, and yeah, unfortunately for me, they just keep going.
Well, I mean, that is ultimately what you'd want, but the other aspect, though, with these billet blocks is they are, I guess, what we call it, serviceable to a degree. We can't run the rings and the pistons directly on the alloy surface. Well, yes, technically you can with a coating.
With an alu-seal block you can, but yeah, they're very brittle. Yep.
Yeah, but I mean, probably the people going down the path of a billet block looking at making upwards of 3,000 horsepower, they're going to be running an iron sleeve, a ductile iron sleeve, correct?
Correct.
So these sleeves, if you sort of get to a point where they're badly worn, or maybe you torch something and it gets a little bit ugly, can individual sleeves therefore be replaced?
100%. Yeah, they just pull out and push back in.
Okay. So serviceable in that respect. So you're going to get some a long life out of that, because this is probably a reasonably rare occurrence. What about in terms of saving the block if the worst does happen and you end up with a rod thrown out through the side of the block?
Yeah, so 6061 is very weldable. 7075 can be welded, but it's not advised. So yeah, they are serviceable like that.
So again, because you've got the entire design, am I right in assuming you could end up basically machining out a patch panel, to use that term, I guess will make sense, and then weld that into the side of the block to repair it and basically bring it back to like new?
Yeah, that's right. So if there is significant welding done on the block, I'd recommend heat treating it again and then remachining everything. So I don't think that a lot of people talk about that, but I definitely recommend that if they're going to be significant welding.
All right, well, let's talk about that, because that is something that hasn't come up on the podcast before. Welding obviously involves applying heat and melting the metal on each side of the weld. So what is the knock-on effect? How does that, what's the detrimental effect on the block material if you've welded excessively to it?
So the heat-affected zone can be quite soft, and when the material is soft, you've got no tensile strength. So definitely recommend heat treating to bring that tensile strength back up. And then it's going to warp though, so you need to remachine everything, not line hone. You need to line bore it.
Okay, cool. Well, let's go through those processes. So first of all, the heat treating process, what does that actually involve?
So it would involve heating the block up, if it's 6061, to around 540 degrees off the top of my head, and then quenching it in water. And then it would need to be held in an aging oven about 180 degrees for about 8 hours.
So this undoes the damage done by welding and basically gets the material all back to an even hardness and strength?
That's it.
Okay.
Correct.
But as you mentioned, that's going to almost certainly end up warping the block. So then it goes back in your CNC machine and all of the key elements get sort of squared away, or is it a bit more involved? You mentioned line boring there, so I'm guessing that's a bit more involved.
Depending on the warpage, it could be done at the engine reconditioners, so normally on manual machines.
All right. Now, coming back to the material again, so the argument for how streetable a billet block is, I've talked to as many people who've said absolutely not, as I've talked to people who are, by all accounts, daily driving these billet blocks with no detrimental effects. And I mean, to elaborate on why there's a potential problem here is the thermal expansion coefficient of the billet aluminium material, as I understand it, tends to be higher than the alloys used for casting, which in layman's terms simply means that they're going to expand more or grow more at operating temperature compared to an OE cast alloy block. The knock-on effect here is that our clearances for our bearings at room temperature when we start the engine will tend to be quite a bit tighter in order to get the hot running clearances where we want them to be. So the danger, therefore, is that if the engine is driven hard when it's cold and it's still warming up, we don't have enough clearance and we can do some damage. So just to sort of get that background out there, I guess for a start, do you agree with this? Is this a problem, or is it a bit of a storm in a teacup?
I can only really talk about my billet blocks in this case, but what I normally do is take the manufactured block from Subaru or Nissan. I then put it in the oven with my billet block. I then very accurately measure the key components, such as the main bore diameter. I'm not finding much difference at all between the cast version and the billet version. Where I think people do run into problems is specifically when a billet block's replacing, say, an iron block. Say with an RB, for example, everyone's used to building, the iron block. They've got their own bearing diameters that they go to, and then once they switch over to a billet, that's when things can be a problem, especially with deck growth. But replacing a cast aluminium block with a billet aluminium block, I think that's a bit of bullshit.
Okay, so essentially it's a bit of a learning curve for the engine builder, and what they've done and no works on the cast iron needs to then be tweaked.
Correct.
For the alloy block.
That's it.
So I'm interested here, as a supplier of these blocks, do you offer guidance on those elements to sort of fast track the engine builders that are using your components, or is that sort of almost open you up for some liability if things don't work out and you tend to leave the engine builder to their own devices?
I definitely try and have a conversation with the engine builder and talk to them through what I know works, but I don't normally put anything in writing for that sort of stuff.
Sure. No, I can understand that. I mean, the other thing is, even if we're looking at the world of building factory cast iron or cast alloy blocks, I mean, you interview 5 different engine builders who are all pretty successful, and they've all got slightly different takes on what works and what clearance range that they want to be in. And, I think we, as engine builders, also tend to get a little bit set in our ways, and it may be almost a bit superstitious. You sort of do something for long enough, and what you're doing is getting results and working, and you tend to be sort of very worried about changing that and finding out that maybe that change wasn't what you wanted. So I can see that there would be a bit of a learning curve switching over to billet. One of the problems we see with high boost turbocharged engines is head gasket sealing, and there's a number of elements that kind of stack up to cause these issues. Obviously, with very high cylinder pressures, we're essentially trying to separate the cylinder head from the block, and we've got obviously improved head stud materials that help with that, different head gasket technologies which also help with that. But at the extremes, we sort of can't get away from the fact that we're literally flexing the deck surface of the block and the cylinder head, and potentially providing a path for the combustion gases to escape. What in the billet block aids with head gasket sealing?
Deck thickness, bigger head studs, more rigidity, less flexing.
Okay. In terms of that deck thickness, I guess the question comes in here: if you were a dry block for that matter, with no water at all, obviously your deck thickness is essentially infinite. It's the thickness of the block. Do you get to a point where there's sort of diminishing returns in terms of maybe you've got 3/4 of an inch, 19 mil of deck thickness? Going further doesn't actually aid you in terms of head gasket sealing?
Yeah, I believe so. Yeah, once you start getting around 3/4 of an inch, then she's pretty chunky.
Yeah, okay. What about other elements such as protrusion of the sleeves? Is that something you use, or does this come down to the individual on their own preferences?
This is a pretty misunderstood concept with wet sleeve engines, and I wouldn't mind touching on that. So the wet sleeve, it seats a lot further down in the block than a dry sleeve. So if you do the math on the coefficient of expansion between where the deck is and where the sleeve seats, when they're at temperature, the block can actually outgrow the sleeve. So to counteract that, you definitely need the sleeve protruding past the deck at room temperature, or you need a very aggressive head gasket strategy.
Okay, so essentially, if you don't have that the sleeve protruding proud of the deck surface of the block, at operating temperature, the block's going to actually grow to the point where the block is now above the height of the sleeve. That's what you're saying?
That's correct. So, and when that happens, all the preload of the firing is now gone.
Yeah, understood. Can you give us an idea of how much protrusion we're talking about here? Is it sort of just a few thousandths of an inch?
Yeah, approximately 3 thou. With fitting sleeves, I find a lot of problems with shops from all around the world. They fit the sleeve and then they deck the block straight away. You have to put a torque plate on there. You have to seat the sleeve. Otherwise, you've got a gap under the sleeve, and then you face it, and then the sleeve drops. So that goes for, if you shrink the sleeve in and you heat the block up, it's radially shrinking and also axially shrinking. So you end up with a gap under there about 2 thou. So you definitely need to put a torque plate on it. And also, if that block then goes in the hot wash, the block grows, forces the sleeve out. There's nothing to put the sleeve back on its seat. If you then deck the block after it's been in the hot wash, you will drop the sleeves after fitting.
Okay, interesting. So on that basis, if you are going to hot wash the block, does it need to be hot washed with that torque plate still fitted?
Correct.
Okay. So this sort of comes back to one of the real common problems we always hear about. And I've talked on the podcast numerous times about sleeving blocks, basically fixing one problem, but then creating this other where more often than not, we hear about sleeve blocks where these sleeves drop in operation. And that's a hugely expensive process because the only way to correcting that is basically remove the engine back out of the car, strip it bare, and then have the block decked again, correct?
That's right. So for any of my blocks, for any of the engine builders I talk to, I always say before you deck it, you have to put a torque plate on there. There's no ifs or buts about it.
Yeah, no, that makes sense. Obviously, you've got access to CNC machining equipment. I always sort of thought that was the key element as to whether or not a sleeving operation was going to be successful. And what I'm talking about here is, manually boring the internals out to take the sleeve, getting the height right between all 4, 6 or 8 cylinders. There was some room for error doing that manually versus CNC, but is that the case, or is that not really the issue at all?
I think the issue is people just don't seat them, and then they deck them, and then there's a gap under there that you can't see. And as soon as it gets up to temperature, the fire ring pushes the sleeve down, and
Yeah.
there you go.
So once you've used that torque plate and you've seated everything, it's been decked, that's it, we don't need to worry about it again? Or if that block, I'm coming back to the hot wash element, if that block is then freshened up a year after a year's running or something, and it's sent to the machinist and it's put through the hot wash as one of the final operations, is that still a potential for an issue there?
I always recommend putting the torque plate on it even before assembly.
Okay. Now, you've used that term a couple of times, wet sleeve. Relatively self-explanatory, but for those who maybe aren't picking up what we're putting down, can you talk to us about the differences between a dry and a wet sleeve and why you would choose one over the other?
Okay, so a wet sleeve has the potential to be quite thick. So if you've got the choice of, say, 5 millimeters of iron, ductile iron, or say 2 millimeters of iron and 3 millimeters of aluminium, and you're going to put, say, 5,000 psi in there, you're going to want to choose the iron sleeve, aren't you? So does that sum it up?
Yeah, so a thickness of the sleeve, but this also sort of comes down to how the water flows around it. I mean, I'm only referring here to what little I know about these sleeves as they're installed into factory blocks. And, we could go with a dry sleeve where, as you mentioned there, thinner in the wall. You would machine the factory liner out of the aluminium block, and you've still got that factory aluminium sleeve that the ductile iron is then pressed into, versus a wet sleeve where essentially the entirety of that factory sleeve is machined out. There's nothing left, and it locates in a register at the bottom of the bore. Have I kind of explained that okay?
Yeah, that pretty much sums it up.
Okay, in terms of cooling potential, I mean, I'm guessing here this is a little different when you're talking about a billet block and how you've designed these water jackets, but is there any downside with pros and cons, I guess, of the dry versus the wet sleeve? And I'm talking here about cooling, not the physical rigidity and strength of the components.
Okay, so with the wet sleeve, obviously water makes contact with the outside of the sleeve, but you have to try and get the heat out of the ductile iron, which is not very good at transferring heat. When you've got a dry sleeve in a aluminium block, you still have to get heat through that interface. So yeah, it's all a bit of a muchness, I think.
Okay, so basically the strength and reliability takes precedent over all else. With a block like your VR38, given that is, I'm guessing now, a fairly mature product, it's been around for a while, what problems, if any, did you find in the early prototypes? I mean, what I'm getting at here is how many iterations of the design have there been? What problems, if any, did you find and have to overcome?
So for the first 5 or 6 years, we were just running basically off the prototype. So I spent a long time designing that block, and to everyone's surprise, it just worked straight from the get-go. We didn't have any design revisions at all for the block itself. To start with, we just utilised the factory VR38 cast main cap cradle. When I started making the main cap cradle, by then I was a little bit more cocky and had a bit of a fuck up. The starter motor wouldn't bolt on to the first couple, but after that design revision, we just ran with that for a fair while.
Okay. When you're going through the design process as well, before you're actually ever sort of manufacturing your first prototype component, because obviously at that point there's a fairly large commitment to the cost of the billet and also the machining time. So is there any sort of finite element stress analysis or anything else done in the virtual world before you start manufacturing prototypes?
Yeah, for sure. So we've got some simulation software in-house, but I sub out most of that now because you can't be a guru at everything, and guys dedicate their lives to that sort of software. So I'd much rather deal with them than me having a guess.
Yeah, that makes perfect sense. I mean, on that basis then, from what came back to you, was your original design sound, or did it highlight some potential areas for weakness?
My original design, I thought I'd design it for 2,000 horsepower, but looking at it now, it's more like designed for like 5,000 horsepower. It's way too thick, way too chunky, way too heavy. So the latest design is slimmed down significantly, but the areas where we've removed material from weren't really serving much of a purpose anyway. So
Okay. I just wanted to take a moment out of our interview with Chris and talk about a course that is really ideally suited to anyone who's enjoying the interview so far, and that is our 3D modeling and CAD course. Obviously, this is really integral with what we've been talking to Chris about, and 3D modeling has become so much more accessible, particularly with the likes of Fusion 360 offering essentially free use of the software for personal projects. It's really provided a huge amount of power right at the fingertips of home enthusiasts, and now it's easier than ever to model your own parts and then get them manufactured by a CNC machining shop. This particular course covers the basics of how computer-aided design works. You'll also learn about the design fundamentals, and while you don't have to be a mechanical engineer to design your own parts, it does help if you have some basic understanding of the forces involved so that you can design parts that are fit for purpose. We also cover the basics of solid modeling, as well as the sheet metal modeling tools that are available in the likes of Fusion 360 and SolidWorks, just to name a couple of the software packages that are popular. We also cover assemblies, analysis of your parts, including geometry measurements and mass and analysis tools. We also cover post-processing, specifically part drawing views, dimensions and tolerances, drawing notes and other specifications, and how to create exploded views for assembly drawings. We'll cover advanced CAD, including surface modeling, simulation and finite element analysis, generative design and automated modeling. We'll also include 3D scanning and printing, which we've talked about within our interview already, canvases, 3D scanning and 3D printing. Now, we've also broken the entire CAD modeling process down into a simple 5-step process that you can apply to your own jobs, and this is going to make sure that you don't overlook anything, waste time and waste money having to go back and redo something that you've overlooked. Within this course, we also include a library of worked examples, which is where you can watch the HPA 5-step design process being applied on a real job. And we add to this library of worked examples from time to time as well, so this course will continue to grow the longer you own it. Course is normally valued at $199 US. You can use the coupon code CREST50, and that will get you that course at half price, 50% off, making it just $99.50 US, $99.50 US. Now, even with that discount, you can also take advantage of our 60-day no questions asked money back guarantee. So if you purchase and for any reason at all decide it wasn't quite what you expected, let us know and we'll give you a full refund of the purchase price. We'll put a link to that course and the coupon code in the show notes. Let's get back to our chat now. In that VR38 world, what is it currently that is limiting the power numbers that can be produced? Is it the bottom end, or is it the heads?
it's the crankshaft. The crankshaft's horrendous. So one of the TX2Ks, I was standing on the line with Ken Gummis from ETS, the engine builder. The very first pass off the trailer, Ken looks at me and says, if we pull that down now and mag the crank, it's cracked.
How many passes will it do after it's cracked? There's a reason for me asking this. So I kind of found back when I was drag racing my old Evo, we bought a billet crankshaft, which back in the day there weren't a lot of options for the 4G63. Sounds stupid now where everyone's making parts for them, but it was a hugely expensive exercise. And we ended up pulling the engine down for a bit of an inspection and freshen up at the end of the season. And the crankshaft, as you do, we got that crack tested, and it had cracked through the fillet radius on a few of the journals, which obviously is not what you want to see. And then it sort of comes to, as soon as you know that it's cracked, you can't in good conscience put the part back in. We ended up in a pinch actually running a factory crankshaft because time and money just didn't allow us to get another billet before our next race meeting. And we ran, I think, 3 or 4 race meetings with a factory crankshaft in it. And at that point, we were probably 1,100 wheel horsepower, 10,500 RPM. So we weren't messing around, not the sort of numbers people are making these days, but it wasn't chicken feed either. And we pulled that down and the factory crankshaft had cracked, at which point you sort of sit back and scratch your head and think, well, billet crankshaft, $5,000. Factory crankshaft, I think maybe I was paying $1,000 or $1,200 for them. You know, it's hard to justify that billet. And the other just side anecdote there with cracked components, back when I was running an Evo 9 that we built for a customer here in New Zealand, and he wanted to take out the late model Evo world record, which at the time he did. We were making about 1,000 wheel horsepower out of that car, ran 834, 170 mile an hour. And what we found is the crown wheel and pinion and the center differential would crack the crown wheel through the base of every single tooth. Visually, you don't need to crack test it. It was pretty apparent. And so part of our maintenance was every race that went to, it had a brand new crown wheel and pinion fitted to it, which was not a cheap exercise. The components were expensive from Mitsubishi, no aftermarket components, and also the labour involved. So it was quite an expensive exercise. But that's what we did. And then there was one race meeting we took the car to. It did one run, and then it poured with rain, so we're back on the trailer. That was the end of the meeting. As a matter of course, we ended up pulling the gearbox apart, and that one pass, that one launch, already cracked through every single tooth. Again, you sort of sit back at that point and scratch your head and think, well, if it cracks on the first pass, and maybe normally we're doing 8 to 12 passes between replacements, sort of how many passes can it do? Is it doing 12? Will it do 20? Or will it do 50? But again, once you know that thing's cracked, it's very hard with a clean conscience to go and put it back together and sort of hope. Well, you got any sort of feedback on that?
My thoughts on that are some of these high-end, and I say that in quotation marks, crankshafts, they're cut from vacuum arc remelted steel. Now, vacuum arc remelted steel is meant to be the high-end stuff, but that's top poured electrode in a vacuum, which there's no such thing as a perfect vacuum. So it's just dilute air. And so what happens is you get an oxide skin forming when the steel is actually being made. The components are already cracked before they go into service. And that's a major, major issue. When a little bit of a stress is applied to it, that's when the cracks show up, but they're already in there to start with. Yeah, so.
But currently, no better process?
There are better processes, and I believe some of the other crankshaft manufacturers are using electroslag remelted material now instead of vacuum arc remelted, which helps significantly. But yeah, I think I've heard on your podcast before other people dealing with products that are cracked before they go into service, and I believe that is from the vacuum arc.
Okay, interesting. Yeah. Don't go too deep into the metallurgy personally, so interesting to get that perspective. I mean, a lot of this as well with the design of that VR38 crankshaft, or the V6 crankshaft in general, is really around the sort of, would you call it, a compromised design of the big end journals anyway, because they don't share a common journal for two cylinders, like a V8, for example.
Yeah, the split journal, the cross-sectional area between the split journals to allow even fire. Yeah, that's a weak point.
All right, well, let's move on and talk a little bit about, well, this is an interesting angle given that you're a CNC shop, but you're actually alluded to cast blocks but aftermarket cast blocks, and we've also got a cast aftermarket cylinder head for the Subaru EJ that we're going to talk about. So, yeah, I mean, on face value, sounds like a bizarre angle for a CNC machine shop to take. What's the impetus behind that?
So making billet blocks, we've been doing it for a long time now, and I've processed hundreds of tons of swarf. It starts to get a bit ridiculous after a while, the amount of swarf that goes out the door. And also the cycle time on the machines, like making the billet cylinder heads for Subaru Motorsports. The cycle times are through the roof.
What are we sort of talking? Give us put some numbers around it.
Some cycle times are 15 hours.
Yeah, okay.
Lots of small tools, 5-axis tool paths. The machine's just sitting there buzzing away, at 12,000 RPM, not removing much material, just tickling material out. So that's why we decided to look at high quality castings.
Okay, so I mean, again, most people these days, with a cursory understanding of the offerings out there in the aftermarket, would tend to think that billet is the ultimate, it's the top shelf option. Is that the case, or is a properly designed and manufactured cast block able to compete or even beat a billet block?
There's another South Australian billet block manufacturer that has the hashtag cast ain't fast. We're out to prove them wrong.
Okay.
But to do that, we design everything in-house. So we design the patterns, we design the mold assembly, we design how the molten metal flows, we design how the casting solidifies. We leave as little to the foundry as possible.
All right, so let's just talk about sort of efficiencies and sort of, I'm guessing here that billet manufacturing would be better suited to small scale production.
Prototypes, yeah.
Prototypes, yeah. So where there's a lot more expense involved in the patterns, etc., for casting, so it's going to lend itself better to mass production. Is that about right?
100%, that's correct.
And could you give us an idea of where that crossover is? If you're going to, I don't know, let's say for example, you're intending to produce greater than 100 blocks at that point. Cast is a no-brainer, or is it not quite that cut and dried?
No, I believe so. Yeah, anything over 100, you'd want to look at casting.
Okay. So again, casting, I think probably has a bit of a checkered reputation because of all these factory cast blocks that we have so many problems with. Where are the real problems with why these OE production blocks actually fail at the power levels we're now asking from them, and what are you doing to fix that with an aftermarket cast block?
So the aftermarket castings looks to improve all the problems from the factory blocks and heads. So when the engineers were designing the castings to start with, racing wasn't top of their list. There are things on their list are emissions and how to make the product as cheap as possible. That's not on our list. We don't care how much it costs to make a quality product. We don't, care about fuel economy, and even weight to a certain extent is quite low. We're looking at reliable, high strength castings.
Okay. The actual material that you're using for casting, we talk about cast iron or cast aluminium. But I mean, then the materials themselves aren't all made equal, are they? Like if we're talking about aluminium, it's an alloy with different materials in it. I'm guessing when you're casting, you've got the ability to specify exactly what that alloy consists of. Does that give you an advantage?
Yeah, for sure. So we're experimenting with different casting techniques and also different alloys. We're trying not to get too exotic at the moment and more concentrating on the techniques of the casting instead of just the alloys, because a lot of foundries out there, they just literally just plop molten aluminium down a hole. And when they do that, they entrain a lot of air and rubbish. And so you could have the strongest alloy in the world, but if you separate it with a layer of oxide film in between that, it's just going to crack anyway.
So is this a case of choosing a high-end foundry that are able to work at the level you need, or is it more involved with the process?
We try and handle all of it, and then the foundry that we choose to use, we just try and convince them to be on board with our process.
Okay.
I use a lot of John Campbell's methods. He's a very well-renowned casting scientist. He designed the Cosworth casting process back in the 70s.
In terms of the patterns, if you like, that go into making a cast block. Can you talk us through how that all works? What are you actually providing to do that? I mean, maybe even give us a high-level view of the casting process, because I've got a very basic understanding of it, but certainly I'd like to know a little bit more.
All right, so a pattern is normally made from tooling board, which is like an engineering plastic, polyurethane. It's very stable, so it doesn't move much at different temperatures. We then machine the shape of the part that we want, and then sand is packed around it, and then you end up with a piece of sand which has got the shape that you need in it. It normally consists of multiple pieces of sand that all comes together to provide the whole mold assembly.
Okay. Sounds like quite a involved process of actually getting that pattern all assembled, ready to pour the molten material into it.
Yeah, so the pattern itself is, you can use it many times, say hundreds or possibly even 1,000 times. So the pattern makes the mold, and then the mold is only used once.
Okay. And then that mold is just sand. So I guess, again, the sand can actually be recycled as well.
That's right, yeah. The sand can be thermally reclaimed or mechanically reclaimed.
Right. Now, if we sort of look back at some of the older cast blocks, and I'm talking here maybe sort of old American iron V8s, etc., one of the problems that is known as core shift, where the patterns or the molds have actually maybe not been aligned correctly, and you can end up with a block that looks like every other block, but if you actually get down to the details, maybe one of the bores is thin on one side and thick on the other. I kind of grew up with later model Japanese engines, and that's kind of what I learned engine building on. I think the techniques and technology at that point, 4G63, SR20, etc., maybe that improved a little bit, and that was less of an issue. How much of a problem is this when you're designing your aftermarket components, making sure you don't suffer from core shift and everything is exactly where you need it to be?
So to start with, it's quite easy when you've got new tooling. I think a big problem with the factory stuff is their tooling would wear out, which means that the core's got a bit of slop, and it's up to the operator. It's operator dependent, which, on a Friday afternoon, they're just throwing it in there, which means the core's hard up one way.
Yeah, care levels out the window.
Yeah, potentially, where we're dealing with new tooling. Yeah, but it's certainly a major priority that we can align the casting on the CNC machine to know where that core is.
Yeah. One of the big advantages that I would expect with the casting technique is it's going to be much, much easier to have a elaborate and well-designed water jacket in the block, as opposed to what is possible to do with CNC machine billet, or am I off the mark there?
It is a lot easier to get a complex shape in there, but unfortunately, everyone wants a bigger bore, everyone wants bigger valves, everyone wants more material, so you end up with super complex thin water jackets, which can be problematic.
Yeah, okay. Now, if you were to offer your billet variant VR38 and a cast variant VR38, just for example, are these two products designed for completely different markets? Are we going to see the likes of ETS replacing a billet block with cast, or is this more a high-end road car application?
At the moment, it's more of a high-end road application until we can get our processes and alloys sorted out for the hardcore drag racing guys.
Sure. And could you give us a sense of the cost difference between a billet block and one of your cast blocks?
Straight away, you'd be looking at half.
Oh, well, okay. Yeah, so that's a pretty significant saving.
Yep.
All right, let's move on a little bit. One of the reasons that we've actually got you on the podcast is we bumped into you at World Time Attack, where you were displaying on the Platinum Racing Products stand a cast alloy head for the Subaru EJ, which caught my eye and has some interesting features. So again, can we start with, I think it's probably pretty obvious by this point in the conversation, but why you went down that cast route for the EJ head versus billet?
Yeah, so when people found out we were making the billet heads for Subaru Motorsport, I was just getting smashed with emails and phone calls. When can we get these heads? When can we get these heads?
Just to clarify there, this is for Vermont Sports Cars in Canada.
They're in Vermont, so that's right next to Canada.
There's a hint in the name actually. I'm just showing my geographical ignorance. But we have had Dan on the podcast before, so they're building cars for the likes of Travis Pastrana and building the rally cars for Subaru in North America, correct?
Yeah, that's right. So we started off making the billet blocks and heads for the Red Bull Rallycross series, and then they found a lot of reliability with them, so they started using them in the Gymkhanas, and yeah, that's obviously pretty successful.
Yeah. So this is a bit of a can of worms when I ask a question like this. Where's the reliability problems in a Subaru cylinder head?
Yeah, good question. So a lot of people drill out the heads for M14 studs instead of M11. So you've got two problems there. You've weakened the fastener column, taking out material, and then to tension an M14 stud correctly, you're then putting massive clamp load on a thin walled fastener column. So you're just going to crush the head and crack between the combustion chamber and the bolt hole, basically.
So this is one of those common scenarios we see in the aftermarket world where we do something to fix one problem and inadvertently create a separate issue, which is often just as big of a problem as the one we were originally trying to fix.
For sure.
So essentially these cylinder heads with the 14mm head studs have a relatively limited life expectancy before they'll crack.
They certainly do. I believe Subaru were getting 1 weekend out of a set of heads.
Wow. You've got to think as well, this isn't a factory head. This would be also heavily worked, CNC ported, all of the fruit that you could think of, and then it becomes a throw it in the bin product at the end of a weekend's racing.
Correct.
All right, so you're making these billet heads for the motorsports cars. What were the changes that you made? Obviously, again, billet, you can pretty much do whatever you want. What were the changes that you made to fix some of the other shortcomings of the Subaru head?
So the Subaru heads have got a dogleg exhaust port to dodge the cross member. So that straight away was out the window. Now all the exhaust ports are straight out.
What's the issue? I mean, people who haven't seen a Subaru cylinder head could probably go and Google an image of dogleg exhaust port to get a sense of what we're talking about. It's obviously a bit difficult when we've got an audio-only platform here, but what does that actually create in terms of limitations or downsides with the head flow?
It just basically means that not all cylinders are equal. You've got two cylinders which the exhaust is straight out, and then you've got two cylinders where the exhaust has to take a bit more of a tortured path to get out.
Yeah. And also, essentially, the distance from the center of the exhaust valve to the flange surface is significantly longer on those dogleg ports than the straight out ports.
For sure, yeah.
Okay. A little knock-on effect here that I just wanted to bring up. This is something that I don't think a lot of people really give too much thought to, but in high-end builds, drag cars in particular, we quite often see exhaust gas temperature sensors being used in individual exhaust runners. And the idea is it sort of gives us a bit of a glimpse into the exhaust gas temperature, obviously, which in turn gives us an understanding of what the combustion temperature is going to be. So these are useful for a variety of reasons, but probably one of the more common is it allows us to do individual cylinder fuel trimming. Basically, the exhaust gas temperature will be influenced by the air-fuel ratio. So if we see a discrepancy, we can jump to the conclusion that the discrepancy in EGT is a result of the discrepancy in air-fuel ratio. Now, again, we assume that every cylinder runs the same air-fuel ratio, but for a variety of reasons, that may not be the case. And when we're starting to put out really, really high specific power levels, our tuning envelope becomes narrower, so we don't want those discrepancies. So that's the idea behind EGT, but the bit that's really easy to overlook is that in order to get useful data out of those exhaust gas temperature sensors, they all need to be mounted the exact same distance from the center of the valve. And the reason for this is the further the exhaust gas travels, the more temperature it loses. So we're not comparing apples with apples. And the other one, which is a little bit less relevant to our conversation here, is the protrusion of the EGT sensor into the exhaust runner also needs to be the same across all of the cylinders. So straight away with the EJ, that gives us a problem because, we could fit the sensors the same distance from the flange, but that doesn't fit them the same distance from the center of the exhaust valve. So straight away, even when everything's running properly, we're going to see that discrepancy. So I just wanted to fit that in there because I think that's something that a lot of people overlook. So you fixed it by just going with a straight port on all 4 cylinders, correct?
Yeah, that's correct. And also on the test bed, the local car, the S&J Automotive, they're running our cast heads for testing. They've got even EGTs now, which is pretty much unheard of, as you said, for an EJ.
Yeah. The knock-on effect, of course, is that now a production off-the-shelf aftermarket exhaust manifold is no longer going to bolt up.
That's correct. And yeah, that's unfortunately the only thing that's not compatible anymore. Everything else bolts up but the exhaust manifold.
One of those areas, though, where the downsides were worth it for the potential performance improvement.
Oh yeah, if we brought out an aftermarket head which still had the dogleg exhaust port, the internet's just gonna roast me.
Yeah. All right. So what other changes were made to the factory geometry specifications?
So much thicker deck thickness, much thicker fastener columns, as we touched on before. We have got a massive CFM increase for people that want to try and set world records. We designed the casting. We maxed it out to start with, the architecture, so we can got 420 CFM where required. But I don't think the platform is ready for that yet. To utilise 420 CFM, you'd have to have a 3-litre revving to 12,000 RPM or something like that. But
porting cylinder heads is definitely not something I've got heavily involved with, and we've had people who are specialists on the podcast in the past, but it's easier to look at numbers and sort of think, well, bigger's better, but it's not just airflow in terms of CFM that's important, it's also the air speed, correct?
That's correct. So currently I'm not offering that one just yet, so we've dialed it right back down to sort of more like 350 CFM.
Okay. Now, at this point, you've got these billet heads that you're doing for VSC, who they're a proprietary head, so you can't actually sell those to others, even if they come along with a big old suitcase of cash. So this was the impetus behind going down the cast path, taking a lot of what you knew worked for the billet heads, but putting them out in a cast package that's more affordable and can be mass produced.
That's correct.
Okay, in terms of the design cycle for that head, how long does it take between sort of the initial idea and a production ready part that someone can purchase?
With the EJ head, which was our first casting project, it took years, to be honest. I initially just approached a foundry with some CAD and let them design the runner system. And when we got the heads back, they were just sieves, basically. They just leaked very badly.
Perfect.
Even after Loctite impregnation process, they just leaked. And that's why we decided to learn how to do it all ourselves.
Is that sort of, I would assume not an expected outcome from going to a foundry?
Most foundries just cast basic things, they're not used to casting complex cylinder heads, especially multi-valve cylinder heads. There's some complex shit going on there.
Yeah, sure. No, understood. All right. Again, an interesting direction that you're a CNC shop, yet you're tending towards cast. Obviously, we've talked about the reasoning behind that, but once you've got these bare cast heads back from the foundry and a foundry that's turning out something that isn't a sieve, that's still nowhere near ready to be bolted onto an engine, is it? So can you talk us through the finishing processes and how your CNC equipment is still being utilized on these heads?
Yeah, so I touched on it before, but a big thing is the alignment of the core to the datum on the machine. We need to know where that core is before we can do anything. We actually cast these heads ambidextrous, the Subaru heads. They're cast so they suit a left hand and a right hand, and then the machining dictates which hand they go. So there is still significant machine time currently, but we're looking at bringing that down in the future.
But that simplifies, you don't actually have to have two completely separate sets of patterns for the two heads.
Yeah, that's right.
Okay, that's an interesting way of going about it. Makes sense. In terms of the porting, you mentioned, sort of you've limited around 350 CFM at this stage. What are the options for the customer in terms of that porting? Is it, purchase it as cast and then a range of porting profiles that are CNC applied, or talk us through that.
Yeah, so we'll be offering the heads as an as cast version with super small chambers and smaller ports so people can do whatever they want. We also offer a CNC ported version, and eventually we'll be offering fully assembled heads.
So far we've talked about the VR38 block, but just wanted to mention that you've also obviously got a Billet EJ block as well, correct?
Correct.
Where are the, again, this is a bit of a can of worms potentially, where are the problems with the factory cast alloy EJ block that you needed to address?
Okay, so the factory EJ block, well, most of them out there, they're high pressure die cast, which leads to very poor mechanical properties. They've got an open deck, which is not good for cylinder pressure and head gasket sealing. So we will be casting an EJ block very soon, but we sand cast and higher mechanical properties. The main tunnel on the Subaru block is the real problem because the blocks are so soft, they just wander everywhere.
Yeah, and I think anyone who's pulled apart an EJ block that's been making even moderate power would probably have witnessed the fretting marks that we tend to see on the mating faces of the two block halves. I mean, the other one that's always interesting is if you go and fit a set of ARP case bolts to an EJ block and torque them up to ARP specification. Generally, you won't actually be able to turn the crankshaft because it distorts the whole main tunnel, correct?
Correct, yeah.
Obviously, we can get around this with line honing the block and making sure that main tunnel is back to perfectly round and concentric. But, I mean, it shows how much distortion there is in the block.
Yeah, the blocks are basically made out of cheese. So they're made to a price. They're not designed for racing, hence the reason why Subaru Motorsport came to us for a billet block.
Yeah, fair enough. That Billet EJ block, is that also sort of proprietary, or is that something that you can sell to customers?
No, we sell the Billet EJ block all around the world.
Okay. All right, Chris, I think we'll move towards wrapping this conversation up. And we've got the same three questions we ask all of our guests. The first of those is, what's next in the future for you and specifically Crest CNC? I mean, maybe you've been around for a fair while already. Obviously, some big changes over that time, but what's the sort of the 5-year plan look like for you?
So we'll be looking at developing better casting techniques and different alloys and continuing the process of converting from billet to castings.
Okay. Any other manufacturers' products sort of on your radar that you think are worthy of development?
So we'll be casting the EJ block very soon to match the cast EJ heads. We're casting the RB block currently, and we'll be casting the RB head early next year as well, if not this year.
I think that'll be definitely a game changer for that RB world because it is increasingly difficult to get hold of good raw castings for those now.
Oh, yeah.
Okay. All right, next question. Is there any advice you'd give to a younger version of yourself or maybe one of our listeners out there to help perhaps fast track your career, get you to where you are faster, or maybe avoid some of the pitfalls that you've seen through your career?
Specifically, if I was talking to myself, I would avoid business partners. The first business partner I had, I'm still really good mates with, so everything's good there. But the second business partner ripped me off pretty badly, so definitely avoid business partners if possible. Yeah,
it is a tough one. I mean, I've probably got a different take on that, but obviously only through my own experience. For those who are aware of High Performance Academy's backstory, Ben is my business partner, and we've been in business now for probably about 12 years. And prior to that, he worked in my old performance workshop as my operations manager for probably about 3 years. And, fingers crossed, touch wood, our relationship has been incredibly strong over that whole time. Just like anyone, we have our moments, there's our ups and downs, but we always sort of work through that. But I am also very well aware that we're probably the exception, not the norm. So I get what you're saying. What I'd say is it's a bit of a case of understanding what your skills are and what your lane is. So what I mean by that is I don't think High Performance Academy would be what it is today if it was left solely to me. My lane is very much the technical side of the course production, these podcasts obviously, and that just draws on my own background and experience running a performance workshop and just doing these things for 13 years, whereas Ben, he is very much the technical side of the website, the marketing side of things. And, there's a synergy between us. Together, the whole is more than the sum of the parts. But I think one of the areas where partnerships don't work is where you've got a very significant overlap on the skills. And, both are trying to do this one task. I think if you can stick to your own lane, that's going to give you the best chance of success with a partnership. But I will agree, tread very carefully if you are going down that path, and make sure that you are very, very careful before you jump into business with someone, because it's very easy to get into business with a partner, much, much more difficult to get out of it if you realize things aren't going correctly.
Oh, yeah.
All right, Chris, last question for today. If people want to follow you, see what you're up to, how they're best to do so, what are your social media accounts?
Chris CNC on Facebook and Instagram. I've also got a TikTok account now that I'm starting to upload some stuff to.
Cool. So a few little dances for the TikTok followers?
Not personally, mainly just the machine.
Probably for the best, I think.
Yeah.
Well, as usual, we'll put links to those accounts in the show notes. Look, I really appreciate your time today, Chris. Great to get some insight into the products and a slightly different angle compared to most of the CNC manufacturers we talk to, where you are going down this path of casting, but for some very obvious reasons, as we've discussed. So thanks again, and we look forward to seeing some more high performance aftermarket cast products coming out of your workshop soon.
Thanks again for having me.
If you enjoyed this episode of Tuned In with Chris, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Chris from the United Kingdom, who has said, second to none, quality content for the automotive enthusiast. Even though I am a PhD student in combustion research who has worked in high performance automotive industry, I continue to learn from most episodes. The technical content is made approachable and presented in an understandable way, and this shows that it is not necessary to obtain an engineering degree to comprehend the advanced technical content covered. Well, that is high praise from a PhD student, so I really appreciate that, Chris. Great to hear that you're still getting benefit out of these podcast episodes. And as a thank you, if you get in touch with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school, and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.